Okay, so let's start. The last thing that I talked about in my last lecture was the fact that when we move from flat space to curved space, we have certain sort of like a transition from the partial derivative to the covariant derivative. Now, what we're going to do is we're going to sort of define the geodesic equation using the covariant derivative, because as we saw, the covariant derivative is very useful in the sense that it concisely tells you how you're computing a derivative in a non-trivial spacetime, right? So therefore, it would be essential for us to derive the geodesic equation, which is again essential for us to know how a particle is moving in a non-trivial space in terms of covariant derivatives. So in that case, I will define something first, which is called a parallel transport. Now, in GR, basically, when we talk about flat spacetimes, a parallel transport simply means that you're translating a vector along a curve while keeping it constant. Okay, so more concretely, we can sort of consider a vector. Let's say we have a vector v mu, and we want to traverse it along a curve. Let's call that curve x mu, which is parameterized by lambda. Okay. So if its components, if the vector's components don't depend on lambda explicitly, then we can write the derivative of the vector with regards to lambda, which I can write as a 0, right? So this, again, I'm computing it in flat space. I have not arbitrarily defined any sort of covariantness over here. I also have defined the derivative as a partial derivative, so therefore this is in flat space. Right, so therefore, if I have a vector, again reiterating, and I am computing it along a curve, and if the vector's components explicitly don't depend on lambda, then the derivative should give me a 0. And this is what I call a parallel transport. Okay, so I'm parallelly transporting the vector along the curve without changing it. Okay, so in that case, in curved spacetime, I can now generalize this using a covariant derivative, and I can write the covariant derivative with d. And this would assert the following relationship. And this would equal to 0 if, again, I'm parallelly transporting it in a curved spacetime. Okay. Now, I have arbitrarily written this for a field, which is general. Can you hear me properly? So I have arbitrarily generalized this for an arbitrary vector field. Now, you can analogously define this equation for arbitrary tensors as well. And in that case, I can write out the covariant derivative in the following way. And the equation of the parallel transport that I've written over here will just boil down it once I expand the definition of the covariant derivative over here, introducing the Christoffel symbols and so on. And I will get this particular equation. Now, this tells us that the components of the vector will now change along the curve, and this change will be determined by this connection over here, which is the Christoffel symbol. Okay. Now, if you really think about it, what is happening? So we have a certain vector. We can also generalize these tensors. So we have a certain tensor, and then we are traversing it along a curve. Okay, and this curve, well, essentially, when you're traversing it along a curve, you want to see how it evolves as it moves along the curve, right? And that particular evolution is depicted by this particular equation. And the equation essentially is dependent or contributed by the Christoffel symbols. So therefore, the parallel transporting of this is defined by the geometry, right? So if you have let's say, vectors transporting in the curve. And if it is, let's say, in flat space-time, then the curve would just follow with the vector, right? But then if you introduce the crystal symbol in this equation over here, then you would get a certain deviation due to the geometry of space. That is what this particular equation talks about. Okay, so using parallel transport and this idea of equations over here, we can define an alternative definition of the geodesic equation as the curve along which the tangent vector is parallelly transported. So in that case, I can write my tangent vector again. And I want to parallelly transport this tangent vector. So I will abide by these equations that I wrote earlier. And if I substitute v mu as this particular vector, which is the tangent vector over here, and if I write this to be dx mu by d lambda, then this over here, I can just replace it and I can write this equation as v nu covariant derivative with respect to nu, v mu equals to 0. Now this is your covariantly expressed geodesic equation, because essentially this would just boil down to this equation over here, which is the geodesic equation. Now this is of course the same, and concisely you can now determine if your vector is covariantly conserved or not. Now speaking of curvature, and which is something that we're trying to do, right? We're trying to build a certain mathematical set of tools for non-trivial spacetime so that we can incorporate curvature over here, and we can incorporate gravity, because as we saw before, gravity is corresponding to curvature of space. Now this is something that we normally miss out. Like Shadman Bhai said, we actually have all good theories for everything else except for gravity, right? So what we need to do is we need to incorporate this particular gravitational effects into our theory. And how do we do that? We have to define geometry, and which is why we work with GR, because GR is a good tool that essentially tells you how gravity relates with geometry. And that is what we're trying to do here. So in that case, if you need to define curvature, you need to define tensors that give you that idea of geometry. And for that, we're going to define now the Riemann tensor, which essentially gives you an idea of geometry. Now, there are many ways you can derive the Riemann tensor, but one particular easy way, I think, is to find the commutation relationship between two covariant derivatives, which is through this relationship. So you find the commutation relation between two covariant derivatives. And of course, for this, you need a test function. So I'm going to apply it on an arbitrary vector. Let's call that vector v rho. And this just means that I'm acting, the covariant derivative with respect to u first, nu, and then vice versa. Okay, so I'll just write that down. So this is what it essentially means, right? And now you can break these covariant derivatives out in our definition of the covariant derivative. I think I wrote it somewhere over here, this one, right? So here you see that I have an expansion of the covariant derivative, which is basically an amalgamation of the partial derivative with an addition of the Christoffel symbol term. So what we can do over here is that we can expand all of the covariant derivatives and then compute that on the vector we're talking about. So let's do that. And I'll just write this simply so that you can follow it. But then again, the whole derivation is in my notes, so you can refer to it later if you want. So first comes the partial derivative. So I'm breaking this part down. So I'm breaking this part first. So therefore, this part should give me one partial derivative and one Christoffel symbol term, right? So therefore, let me first write down the partial derivative term, and then the Christoffel symbol term. And then you will get another one for this term over here, this one, right? So I have another covariant derivative, which I can also expand in a similar way. And I will get, again, another partial term over here. So I can write this as d nu on V some Christoffel term over here, which I will get as rho sigma. And I will follow this again just by switching the indices because I have a commutation relationship. Okay, so essentially, finally, after all the work done and after you compute all the derivatives, what you will finally get is the following expression. So I'm just writing it down so that I can refer to this later on. I do not suggest you to work it out all by yourself because it might take some time, but I do suggest you to look into the derivation that I have in my notes so that it's easier for you to, refer to it later. Now, okay, so this is finally what I get. Right. So over here, I see that there are a couple of terms which are first derivatives of the Christoffel. And then I have some combination of the Christoffel symbols. And then I have this thing over here, which is essentially telling me that the two indices that are at the bottom of the Christoffel symbol are not symmetric. They're antisymmetric. Okay. Now I can redefine this. And I can write the commutation relationship that I just found in terms of two tensors. And those two tensors are given or defined as the following. Sigma. So let me write this as a new tensor. And I can just put the 2 inside my definition, and I will have this to be the following. Okay, so over here, I have defined 2 particularly new definitions of tensors. This term over here basically amounts to this term over here. Let me, okay, so that's fine. And this tensor over here, I'm redefining it to be this tensor over here. Now, this particular tensor with R is the Riemann tensor we're talking about. And this tensor over here is called the torsion tensor. Okay. Now, in general relativity, we know that we are working mainly on torsionless manifolds, right? So what torsionless manifolds mean essentially mathematically is that the two symbols that are at the bottom of your Christoffel symbols are symmetric. That means if you switch up their order, they will still stay the same. In that case, if that is true, then that means that you cannot apply symmetry over here, and therefore this goes to 0. And since it's torsionless, the torsion tensor would also go to 0. And therefore, the commutation relationship finally boils down to this particular definition. And this equals to only in the definition of the Riemann tensor. Now, what the Riemann tensor essentially does is it tells you the amount of degree to which the covariant derivatives commute, right? So if the covariant derivatives commute, then the Riemann tensor would go to 0, right? And if the covariant derivatives do not commute, then you have a certain degree that depends on what the Riemann tensor is that tells you how much degree they don't commute. Does that make sense? So basically, this should tell you how much they don't commute. Essentially. Okay. So therefore, this Riemann tensor, you can use it to understand the commutativity of the covariant derivatives. And since the covariant derivatives are essentially telling us if you are working on curved space or not, like we mentioned last class, the Riemann tensor should also tell you if a particular manifold is curved or not. So I am talking about manifolds, but I haven't defined what a manifold essentially is, right? So this is something that you're also going to see in the topology and geometry class. In fact, you were supposed to see it yesterday, so I have not included in my lecture notes, but I will still define it here for convenience. So I will just define it very roughly. What manifolds are. Essentially, manifolds are the underlying geometrical space that we're working on, topological space we're working on. That would be better wording. So in that case, manifolds abide by, and specifically the manifolds that we're talking about abides by some conditions. And we are typically, or GR is typically defined on a differential manifold. And differential manifolds have particular conditions that they abide by. So first of all, they're topological, which means that they are homeomorphic to Rn. Secondly, they have a smooth structure. Now, what smooth structure essentially means that the manifolds are a collection of overlapping atlases that have transition functions that are infinitely differentiable. Okay, so if there is 2 points in the manifold, let's say point A to point B, and there's a transition function that relates the 2 points, that particular transition function will be infinitely differentiable. Okay, so you will have a collection of overlapping, let's call them charts. Charts are basically, you can understand them as coordinate systems. And I can write them as with smooth transition functions between points. So again, by smooth, I mean infinitely differentiable. Sort of like analytic functions. And that is something that we covered last geometry class, I think. Okay. So now let's talk about, now I can actually freely talk about what manifolds are, as in use the word manifold every time I mention something like space. So basically what we're doing is we're working on differential manifolds. And on that differential manifold, I'm defining my general theory of relativity. Okay. Okay, so now I move on to attributes of the Riemann tensor. So I understand that the Riemann tensor essentially tells you to what degree the covariant derivatives do not commute, right? And also the Riemann tensor should then therefore give you an idea of curved manifolds. So in that case, I want to attribute this Riemann tensor, and I can find characteristics from these Riemann tensors, and they will extend to particular objects, and them I will call the Ricci tensor. And the Ricci scalar. And these are just extensions from the Riemann tensor. Okay. So given the symmetries of the Riemann tensor, which I'm not jotting down over here, there are 4 particular identities that the Riemann tensor abides by. But due to limitations in time, I don't have the time to write them down. But we understand that there are particular symmetries that the Riemann tensor abides by, and due to those symmetries, I can have a particular contraction which would eventually give me the Ricci tensor. So essentially, I will have R mu nu, which I'm calling the Ricci tensor, and it is a contraction of the Riemann tensor in the following way. So you see that the contraction is happening on lambda. And this, from the definition of the Riemann tensor that I wrote from here, you can see that আমি যদি এখানে দুইটা ইন্ডেক্সকে contract kori, as in I take, let's say, rho and mu to be contracted, then I can do the same computation in the definition, the broad expanded definition, right? So that should give me some expression. So that expression basically gives you the expression for the Ricci tensor. And essentially what I will get eventually is the following. Yeah, like I said, maybe referring to the lecture notes would be easier for everyone and easy to follow. So this is my definition of the Ricci tensor. Now, you see the Ricci tensor is a combination of the Christoffel terms, right? And if you remember, the Christoffel terms come from the metric. So therefore, the metric again tells you the geometry of space, essentially, right? So in this hindsight, then you can sort of say that if I know what the Ricci tensor is, I can know what the geometry of space-time is. In fact, at least you can tell if it's flat or curved, right? So if you have the Ricci tensor to go to 0, that means all the term over here should combine to go to 0, right? That would mean that I would have a flat space, right? On the other hand, if you don't have the Ricci tensor to go to 0, that means there is some curvature existing in your manifold, and that is a test to see if your particular metric defines curved space or flat space. And we use that typically in GR. When we define metrics, we define this Ricci tensor and see if you have a particular metric that is curved or flat or not. Now, from the Ricci tensor, you can contract it again. In fact, take a trace over, and the trace of the Ricci tensor gives you the Ricci scalar. And basically, you contract two of the indices by adding a metric to it. Now, there are many things I perhaps didn't mention or didn't get the time to mention, is that how you use the metric to contract indices. Maybe this is something that you can find in GR references, okay? So this is something that I didn't mention, but you can use the metric to lower and take indices up. Lower and raise indices, that's the word. Okay, so now this Ricci scalar, essentially, like I was mentioning, that you can use the Ricci tensor as a test, right? To see if your particular manifold is curved or flat. Ricci scalar can also be used in the same manner. However, Ricci scalar can only be used to understand local curvature of a manifold. So if you have the Ricci scalar to go to 0, that means that particular geometry or the particular manifold is locally flat. So locally flat মানে হচ্ছে আমি একটা particular coordinate systemer neighborhood আমি ওটাকে flat বলতেছি. This does not necessarily mean that that particular manifold is globally flat. Okay, so Ricci scalar can be used as a test to see if a particular metric is locally flat or not. On the other hand, if you have Ricci tensor to go to 0, that means that the manifold is indeed globally flat. Okay, that is the two difference between the objects. Now, এটা উল্টাটা হইতে পারে, যেমন for example, you can have intrinsic geometries, right, of manifolds, and if you have intrinsic curvature, that means যে তোমার locally হচ্ছে it's curved. On the other hand, on on the larger scale, it might look flat. I mean, that is something that we do with the universe, right? We model the universe as a flat universe, because when we model the universe, this is something that we will see in my cosmology classes as well. We work with a metric that is a flat FLRW. But of course, we know that the universe is not flat, or we wouldn't have galaxies or galaxy structures, planets, etc. So locally, when you have, let's say, galaxies, they're curved because you have mass that curves the space-time and so on. But globally, when you look at it from a larger scale, it looks flat. You can also have that. It depends on your intrinsic geometry. Okay, so now we are motamoti at a stage where we can derive the Einstein's equation, because like I said before, there are two things that GR works on. The main key ideas is, first of all, we have to know how space-time tells us to move. It আমরা already defined through the geodesic equation. And we have to understand how matter tells space-time to curve, right? And the way we do that is by introducing the Einstein's equation. So this equation will essentially relate the local space-time curvature that happens due to matter. Now, one way to derive this particular equation is through, again, an action, right? Because any sort of dynamic equation should come from the action. And for this particular equation, we use the Einstein-Hilbert action. And what we normally do in this action is we take the action to be an integral of a scalar function, right? And that particular scalar function should be, let's say, a measure of the local space-time curvature. Because আমরা যেটা এখন করতেছি সেটা হচ্ছে যে we are working on a non-trivial space, which should tell you that that particular manifold could have curvature, right? So essentially, if you are, devising an action, again, what is an action? The action should tell you how this particular moves from one point to the other, right? So a particular movement will depend on the geometry, and therefore what the action is defined by should be a function of that particular geometry, and therefore should be a function of that space-time curvature. And of course it should be something that you can derive up to twice, like it should be second differentiable, because as we saw that the equation of motion has to contain a second derivative term, right? So there are two key ideas ekhane. Ekta hocche je you need to have a function in the action that is relating space-time curvature, because like I said, the line element has to matter because of the geometry and all of that. Number two hocche je it has to be second differentiable, because the equations of motion have the second derivative in it. So therefore something that abides by both of these conditions is the Ricci, right? Because আমরা Ricci scalar গুলো দেখছি বা Ricci tensor গুলো দেখছি, they have the derivative terms, and therefore when you take the variation, they should be second differentiable. So in that case, we define the Einstein-Hilbert action using the Ricci scalar. And scalar ta keno? Because like I said, it should depend on a scalar function, which is given by this. So this is the Einstein-Hilbert action, where I've defined G to be the determinant of the metric over here. And there is a factor of minus over here, and this was introduced so that, when you write the volume term, let me just write it down. Introduced so that the volume term, which is this term over here, is invariant under coordinate transformations. Yes. So eta coordinate transform, because we took one of the determinants to be negative, one of the eigenvalues to be negative, right? Because we're working on a pseudo-Riemannian manifold, like I mentioned last class. So we have one temporal component to be negative. So to abide or to basically simplify that equation, we put a minus in front. Okay, so now I have the action done. The next work for us is to vary this, like we did for the equations of motion. So varying it with respect to the metric. And once we do that, we can write the Ricci scalar also as a component of the metric, because the way we found the Ricci scalar was by contracting it with the metric, with the Ricci tensor, right? So I can write this as the contraction of the Ricci tensor, and now take the variation of this particular action with respect to the metric. So in that case, what I'm trying to do is find delta S, and this would equal to the variation of this term again. I wrote the Ricci scalar as the contraction of the Ricci tensor with the metric. So once you vary it, this is what you are going to get. Okay, now we can see, maybe not directly, but the last term over here, we can sort of extend it to a total derivative. Maybe this is not visible from here, but trust me on this, we can do that. We can see that this particular term will look like a total derivative, which means that this term over here, I can write it as a certain covariant derivative, which is a total derivative, where I'm taking x mu as, let's define it as the variation of the Christopher, And yes, so then I will have this term over here. Okay, so this may not be directly clear over here, but once I raise this to a total derivative, this term over here to a total derivative, and assert boundary conditions, this should go to 0, right? The total derivative term. So in that case, this can be dropped from the variation equation without really affecting the equation of motion. So in that case, I can boil the metric or the variation of the metric just to these two terms over here. These two terms. Okay. Now, finally, what I want to do is the next thing that is important over here is to evaluate the first term. So to evaluate the first term, let me just use a couple of facts that works for diagonalized matrices, because here I'm dealing with the metric G mu nu, right? And the way I defined the metric earlier, I said that it is symmetric. That means you can always find a basis where you can diagonalize the matrix. So in that case, let me use some properties of diagonalized matrices to further evaluate the first term. So if I have a particular, let's say an arbitrary matrix, which is M, and I say that this particular matrix is diagonalized, then it is true that if I take a logarithm of the determinant of M, this is the same as taking the trace of the logarithm of M, right? So this particular identity, once I take a variation over it, should give me 1 by determinant of M varying determinant of M. I'm just sort of taking a derivative. And this should equal to trace of M inverse variation of M. Now, let's specify this M to be our metric and take M to be the metric G mu nu, so that the determinant of M actually now means the determinant of G mu nu, which I earlier defined as G. Okay. In that case, the variation of G would then just become G mu nu delta G mu nu, which I can write as minus G mu nu delta. Now I can do this because remember that G mu nu and G mu sigma are inverses of each other, right? So this is true if I have nu and sigma to be the same, right? In that case, they're inverses of each other. So that basically tells me that I can write G mu nu delta G mu nu as just minus, or let me just get rid of the G so that it's easier for you to see. I can write this as just the minus contribution once I take the inverted components. And that is why I have this term over here. Okay, so now if that is so, then I can write the variation of this term. Sorry, this had a square root. And I can write this as, once I vary square root of minus G, it should potentially give me minus of variation of G. And I can use variation of G from here and plug it in over here. And this should give me G by, so the minus goes away. Okay. And I can just compute this, and I would finally get half okay. I think I'm done. And the reason why I need this is because I have a variation of square root of minus G over here, which I can just plug it in from what I did so far. So now incorporating that over here and substituting this particular variation into the action, what we finally find is something that looks very exciting, which is this over here. Okay, does this look familiar to everyone? That means we are one step away from actually deriving what we think this is. Okay. Now, like I said, you use the equation of motion once you extremize the action and set it to 0, right? So that means if I want to set this to 0, this whole thing should be equal to 0, right? So therefore, let me redefine this whole particular term over here, this one, and let me write this as G mu nu, which equals to R mu nu minus half G mu nu R, and call this the Einstein tensor. And this would equal to 0 if I'm considering that delta S goes to 0, right? And this whole thing is the vacuum Einstein's equation. Now, why are we calling this the vacuum Einstein's equation? Oh, sorry. Why are we calling this vacuum? Exactly. So when we define the action over here, we did not imply any sort of implication of matter or any substance that we're putting inside the action, right? We just derive this absolutely from the idea of curvature, absolutely from the idea of geometry, right? Therefore, geometryটাকে কি কার্ভ করতেছে সেটা আমি এখানে লিখি নাই। ইনফ্যাক্ট কার্ভ আদৌ করতেছে কিনা সেটাও লিখি নাই, আমি আরবিট্রারি জাস্ট জিওমেট্রি ইউজ করে আমি অ্যাকশনটাকে ডিরাইভ করছি। And since I'm not adding anything into my system, matter হোক, particles হোক, whatever, therefore this is vacuum. Okay. And we can further imply adding matter. So ওটার জন্য যেটা করতে হবে সেটা হচ্ছে আমাদের যে এক্সিস্টিং অ্যাকশন হিলবার্ট আইনস্টাইন হিলবার্ট অ্যাকশন আছে সেই অ্যাকশনের সাথে আমরা জাস্ট একটা ম্যাটারের অ্যাকশন অ্যাড করি। So we can do that by considering it non-vacuum, and I can define my action to be the following, plus some action that introduces matter, and a particular term টা আসতেছে এখানে because this is what is a relative normalization constant of the Einstein-Hilbert action along with the matter action. Okay. So now, next আমাদের যেটা করতে হবে to get the non-vacuum Einstein's equation is to do the same thing that we did with the vacuum one, vary the action, set it to 0, and the other things follow. So let's do that. So I take the variation and I get the following. So maybe I will not write all the details, but the variation will give me something like this, where G mu nu is essentially defined as the Einstein tensor over here, and T mu nu is essentially the energy momentum tensor, where we have defined the energy momentum tensor in this particular way. So this is the variation of the matter part with respect to the metric. Okay, so তার মানে কি? তার মানে হচ্ছে essentially you get the energy momentum tensor from the matter action. So that must intuitively imply that the energy momentum tensor tells you the constituent of your system, মানে whatever matter, particles, energy, pressure, fluid, whatever that you're putting into your action from the matter action is being transported to this particular term that we are calling the energy momentum tensor. So now, of course, delta S goes to 0. And in that case, that will only happen if this whole thing goes to 0, right? And that means that I would have a particular equation that will look like this. Does this look familiar? So what is this K? So we know what that is, right? Arbitrarily, তার মানে হচ্ছে this equation can be solved by any arbitrary constant that you follow from here. But of course, the scales come from the particular scales that you work in. So that particularly is 8 by G by C. Okay. So where you can even set C to 1 if you want. Okay. So here, one of the nice things that comes out is that I think I missed something. Right. So I missed one particular term over here. No, I think it's okay. So now, the next thing that I want to do over here is that I want to take a particular coordinate transformation. Okay, and I want to see if this particular action is invariant under that coordinate transformation. এটা কেন করতে হবে? এটার একটা কারণ হচ্ছে essentially I want to see how it evolves and আদৌ এটা ইভলভ করে নাকি। ওকে, কারণ কোঅর্ডিনেট ট্রান্সফরমেশন নিয়ে আমি দেখতে চাই যে একটা আমি যদি কোঅর্ডিনেট চেঞ্জ করি আমার ফিজিক্সটা সেম থাকতেছে কিনা। And because GR abides by something called diffeomorphism invariance, which just means that if you make a coordinate transformation, your physics or your theory should be invariant under that transformation. I want to check if this action is correct. Okay, so let me make a coordinate transformation, which is an infinitesimal coordinate transformation. So I take x mu to go to x mu minus v mu. And in that case, I will have, and I will see that the metric changes through this coordinate transformation, which is through a covariant derivative. Which is given as follows. Okay. Now substituting this particular variation, this term, in this part, in the variation of the action, and I will get the variation to look something like this. Okay. So again, the variation should go to 0, right? Delta S should go to 0. So if delta S goes to 0, that means that this term over here should also go to 0. Okay. Now, one particular thing that I mentioned, that the Riemann tensor has some identities, right? So does the Ricci tensor, that follows from the identities of the Riemann tensor, but I didn't mention it explicitly. So one of the identities is called a Bianchi identity. Okay, so the Bianchi identity essentially tells you that the covariant derivative of G mu mu, which is the Einstein tensor, is 0, which means that the Einstein tensor is covariantly conserved. That means this goes to 0, right? So if this goes to 0, and for this whole part to be 0, it must be true that this also goes to 0, right? And this hangs together because, of course, I know that covariantly the Einstein momentum the energy momentum tensor is 0, because covariantly energy and momentum is conserved. So therefore, this also implies that this equals to 0, which is testament to the theory that this works. And this is indeed conserved even when I make a coordinate transformation. Yeah, so it's diffeomorphism invariant. No, এটা gauge transformation তখনই হবে if I take a local, মানে আমি এটা locally symmetric কিছু বলি না, মানে I did not assign any sort of local contribution. U1 symmetry কি? What is U1 symmetry? It's a unitary transformation, right? I mean, I did not mention anything about that here. So this can be considered to be a gauge symmetry if I define these particular objects to be local, in the sense that they're dependent on, let's say, a particular coordinate x or t. No, I'm just like a generic infinitesimal coordinate transformation. That's all. Yes, exactly. That is actually very beautifully put, because GR indeed is a gauge theory, because you can get these redundant degrees of freedom. What I mean by that is you can add anything over here and you will still get the same physics. That means anything you put in still gives you the same symmetry. That means that anything, that particular whatever you're putting in, is redundant, right? Even though they're unphysical. If we consider that V mu over here is just whatever term, that should still abide by the conservation laws. That means that this is a particular gauge transformation. Mhm. হ্যাঁ, মানে বিয়াঙ্কি আইডেন্টিটি গুলো আসে বিকজ অফ কনজারভেশন লস, রাইট? মানে এসেনশিয়ালি কেন হচ্ছে, কারণ when you take a variation of this, let's say this, right, what happens is these terms become a total derivative and they go away, যেটা আমাদের অ্যাকশনের ক্ষেত্রে হয়েছিল, যে টোটাল ডেরিভেটিভ টার্ম গুলো কিন্তু থাকলেও they don't affect the equations of motion. So you can have any total derivative term over there, it would still give you the same equations of motion. Therefore they are redundant degrees of freedom. So মানে they kind of go hand in hand. ওটার কারণে আমার বিয়াঙ্কি আইডেন্টিটি আসতেছে, আমার বিয়াঙ্কি আইডেন্টিটির কারণে ওগুলো আসতেছে, and so on. So this is like a complete set of mathematical consistency, you can say. Okay, so now moving on, this is not done yet, right? Because what I've only defined is the Einstein equations for vacuum, in the case that we don't have anything at all, matter or anything at all. And we've defined it if we include matter. But what happens if we include something else? It is called the cosmological constant. So maybe this is something that you are all familiar with. I don't know, but the cosmological constant essentially tells you that the universe expands. Okay, and the expansion of the universe is accelerating now, and we sort of attribute it to the cosmological constant today. Okay, so therefore the cosmological constant addition to the Einstein's equation is important. In fact, Einstein did do this firsthand. In fact, he saw that adding the cosmological constant would be coherent in his mathematics, but he thought, wait, why should the universe expand? Right? Why should the universe expand or accelerate? Because by that, during that time, we didn't know that universe actually accelerated or whatever, or in fact we had anything called dark energy or something that is accelerating the space-time. So he cut it out of his equations, but now we put it back in because we see that it indeed is coherent with the observations that we see today. So therefore, let's see what happens. And what we do is we take a term that is of the form lambda g mu nu, and the reason why we add the g mu nu is to be Lorentz invariant with the other indices that are on the other hand side, right? So let me write down the Einstein's equation over here so that you can relate to it. Right, so we add an extra term over here which contains the cosmological constant. The reason why I have g mu nu over here is to be consistent with the indices on all sides. Okay, so this particular cosmological constant can sometimes be identified as the vacuum stress energy, and this is also something that I think Rakin will talk about in his lectures. No? Okay, maybe I can add something about this in my cosmology lectures, but this is something that you will find for sure in the main school. Right? So anyway, like this is important because, well, essentially this is why we have accelerated expansion now. And to understand cosmology or the universe now, we need to abide by this particular cosmological constant. There is a particular thing in cosmology called the cosmological constant problem. Please read up on it, and it is one of the unresolved problems of cosmology today. And string theory, I think, also tries to attack that particular problem. Okay, so অনেক লো। না মানে it depends on how you're contributing it from a gravitational perspective. So for that understanding, you need a theory that brings standard model and gravity together, which is string theory, right? So string theory perspective, that is what they're trying to do. They're trying to solve this particular cosmological constant problem. And I don't think we will get an answer until we have observational idea about how the cosmological constant should scale experimentally. Okay. So anyway, so like I said, to get this particular Einstein's equation, you need an action that looks in the following way. So again, this term over here, the first term over here is just a normalization constant, where G is the gravitational constant, which I forgot the value of, but it's the gravitational constant. And the action will look something like this, incorporating the cosmological constant into your action. And of course, I'm adding the matter because I have T mu nu on the other side. Okay. So we see that the cosmological constant actually corresponds to a pure volume term, because this is with the cosmological constant term, this is the pure volume term that adds to the action. Okay. Now, are there any questions so far? Because what I'm going to do next will be a little difficult. So if there are any questions so far, maybe we can address them and then I'll move on to the next part. No? Okay. So now, next আমরা যেটা করব সেটা হচ্ছে যে okay, আমাদের GR এর basic কাজ কি? Why are we doing GR in this preschool? That's because the preschool's logo, if you saw, has a black hole in it, right? So therefore, of course, main schooler অনেকগুলো topics will emphasize on black holes. And GR এর একটা beautiful test is black holes, right? So সেক্ষেত্রে আমাদের বুঝতে হবে যে এই ব্ল্যাক হোল গুলা জিআর এ কোথা থেকে আসে। So when we solve Einstein's equation, particularly vacuum Einstein's equation, we will get some solutions that you will see eventually give rise to solutions of black holes. Okay, so one of those solutions is called the Schwarzschild solution of the vacuum Einstein's equation, and we will look into that, and we will eventually try to actually derive the whole thing. So the Schwarzschild solution of the Einstein equations. Okay, so you have to note one thing, that this is the solution to the vacuum Einstein equation. So what the vacuum Einstein expanding to? That's a very philosophical question. I don't know. Because we don't have an idea of the fate of the universe eventually. We can predict depending on, you know, the theories that we have today, but eventually we don't know. If you're wondering, but if the picture in your head, from what I understand, is you have a bubble and that bubble is expanding, and what is it expanding to, right? That's your question. But essentially, we don't know if the universe is indeed a bubble or not, right? Because for us to know if it is a bubble, we need to see that there is a boundary. But we don't know if the universe has a boundary. Some models might tell you that it has a boundary, some models might not tell you, but distinctively you cannot tell if the universe has a boundary or not. So in that case, we don't particularly know where the universe is going. Mm-hmm. Yes, this is something that we're going to cover in cosmology as well. You can have particularly 3 solutions to the metric of the universe, which is flat, open, and closed. So that depends on what type of geometry you're working on. But observationally, we see that the universe is indeed flat on a global scale. Okay. Acha. So if you have any questions about these kind of things, you can, you know, come to the cosmology classes. We will address these very questions. In fact. Okay. Acha. So let's start. So the way we start doing this is by initializing the fact that this is a solution to the vacuum Einstein's equation. And the vacuum Einstein's equation essentially means that you have R mu equals to 0. Similarly, T mu equals to 0. But that would imply that T mu equals to 0. Okay. So r mu equals to 0 মানে কি? It's flat, right? So wait, black holes যদি আমি বলি Schwarzschild solution দিচ্ছে, how could this be flat, right? Because essentially black hole বলতে আমরা কি বুঝি, মানে একদম intuitively আমরা বুঝি যে this is like very high gravitational field that exists at some point. So if there's a high gravitational field, it should mean infinite curvature, right? So to tackle that question, this solution does not actually imply inside the black hole. Okay, this implies right outside, right at the horizon of the black hole. So ওইখান থেকে asymptotically the space is flat. Okay, so therefore Schwarzschild metric is a flat metric. So it's sort of like this if you want to think about it. So let's say this is the black hole and this is the curvature of space. Schwarzschild metricটা হচ্ছে তোমাকে এটুক পর্যন্ত idea, just the space that exists right outside the black hole. What happens inside, we don't know. Maybe some people do know. I don't know. হ্যাঁ আর non-zero value জন্য equations আছে, which is one of them is called the FLRW, right? And you can also have Friedman equations come out from. Then this is something that we will tackle in my cosmology class. Acha, so now let's try to solve this. So we start by defining the most general spherically symmetric line element. And our general spherically symmetric because it's easy to work with, and this is a solution we will see that gives rise to the particular Schwarzschild solution that I'm talking about. So সবচেয়ে general spherically symmetric যদি করতে চাই সেই ক্ষেত্রে it has to be rotationally invariant, because আমি simplistic একটা model নিচ্ছি, right? So আমি ধরে নিচ্ছি যে একটা spherical solution আছে which is not rotating. So in that case I need to consider a particular line element that is rotationally invariant. So in that case, I can write the differentials. So in my note, I wrote the x's as bold. So because I cannot transport the same thing over here, let me just write the bolds as, with a bar. Okay. So this equals to r squared in terms of polar coordinates. And I polar coordinates because, I'm considering a spherically symmetric solution. So it's always easy to work with polar coordinates in that case. Okay. So the most general rotationally invariant line element, therefore, would look something like this. So line element I mean ds squared হিসেবে লিখতেছি এখানে, and আমি arbitrary কিছু functions নিতেছি that can depend on time and also space. The radial coordinate r. So this is the temporal part, and I have the other spatial parts, which I can also define with no. So I will have the mixture terms over here. R dt dr. Now this is very general, and I mean arbitrary function গুলোকে define করতেছি. How much time do I have? 24 minutes. Okay, so now to simplify the radial part over here, what we can do is we can sort of redefine the radial coordinate. Let me write this as, okay, let me take r tilde because I already used the bar. I can redefine the radial coordinate as dtr. In that case, we can collect the arbitrary functions over here, a, b, c, and d, and we can redefine again the line element, then it would look something like this. Now with the redefined radial coordinate, which is r tilde. Now this is going to take some time, so please bear with me. But trust me, the solution will be very satisfying. And this is particularly important for the black hole thermodynamics class that we're having on the 28th by Professor Mahbub Mojumdar. So he particularly asked me to show you this. Okay, so now this is what I have. And now what I want to do is I want to again sort of make a change of coordinates. And আমি এসব কেন করতেছি? Just to make my line element simpler, which I can do algebraically, right? So in that case, I want to introduce a new time-like coordinate, t, let's call this t tilde. And this will be defined by the relationship as follows. Now, there is a particular reason why I am adding phi over here, which I will say in a bit. You see, this basically relates the generic t that we had so far with the new time-like coordinate t tilde. Okay, the reason why I have phi over here is because this is a differential equation, right? And I want to make this differential equation an exact differential equation. So I'm adding a particular integrating factor in front to make this particular differential equation exact. So this transformation using the new time-like coordinate will now give me the term over here. Basically, the old terms which I had as these will now transform to using the new coordinates that I've defined earlier. Okay. Now we can define these functions up front, these over here, and we can say that I have a particular function. Let me take that as exponential of 2 alpha. And let me say that this equals to 1 by a phi squared. And I can do this as long as I can change what alpha is, right? I can make the relationship as long as I can define alpha with respect to phi. And I can do the same for the other term, initialize a certain exponential, e equals to 2 beta. And I can write this as c plus b by 4a. Again, depending on what beta is, I can make the relationship with c, phi, and so on. Sorry, c, a, and so on. No. It's just an arbitrary term that I'm adding to make your particle differential exact. That's all. It's not that potential. Okay. Now, incorporating this, all of this, what we get is ds squared equals to minus e এখানে আমি কিছু চোরামি করছি। একটা হচ্ছে যে আমি মিক্স টার্মস গুলো সরাই ফেলছি, ডিটি ডিআর গুলো নাই, রাইট? এটা কেন? না, এটার অ্যাকচুয়ালি সবকিছু সুবিধার জন্য করতেছি না। there is actually one physical reason for this, সেটা হচ্ছে যে remember that the Einstein's equation comes from symmetric metric, right? Symmetric matrices, তার মানে আমার off diagonal terms গুলো নাই। So therefore off diagonal terms যেগুলো dt dr will go to zero eventually, so therefore আমি এগুলো সরাই দিছি। আরেকটা চরমে করছি সেটা হচ্ছে যে আমি t tilde আর r tilde কে trr হিসেবে লিখছি, just to এটা সহজ করার জন্য করছি, okay, just so that it's convenient. Okay, so now sorry, so that I can define these relationships, is it t এর সাথে t এর relationship and a r এর সাথে a r এর relationship? যদি আগে থেকে লিখতাম তাহলে there would be a discrepancy on which r I'm talking about, right? So যেহেতু আমি আমার পুরো মেট্রিকটাকে ট্রান্সফর্ম করে দিছি to t tilde and r tilde, I can just redefine them as t and r again. That's not a problem, right? Okay. So now I have my line element over here, and আমরা যেটা এখন করব, that since this is supposed to be a solution to the vacuum Einstein's equation, we have to demand that these terms alpha and beta are time independent. Okay, why is that? Because আমি যদি r mu nu কে 0 ধরি, as in which is the constraint for my vacuum Einstein's equation, that must state that alpha and beta are time independent. Okay. And why is that? Because I have some bunch of temporal derivatives in my R mu nu that should eventually go to 0. Okay. So if they are time independent, this important result actually goes by the name of Birkhoff's theorem. Okay. What Birkhoff's theorem essentially states is that any spherically symmetric solution of the vacuum Einstein's equation, or let me just call them field equations, of the vacuum field equations, must be static. So static means independent of time. Now, next কাজ কি আমাদের? অনেক কাজ আছে। সেটা হচ্ছে যে we need to compute, আমাদের এখন মেট্রিক চলে আসছে, রাইট? আমাদের d স্কয়ার্ড আছে, d স্কয়ার্ড মানে হচ্ছে আমাদের মেট্রিক আছে, মেট্রিক এখন আমরা পেয়ে গেছি। নেক্সট কাজ কি? মেট্রিক থেকে আমাদের ক্রিস্টোফেল গুলো কম্পিউট করতে হবে, রাইট? বিকজ ইফ ইউ রিমেম্বার দ্য ক্রিস্টোফেলস ওয়্যার ফাংশনস অফ দ্য মেট্রিক, সো ওটাতে আমি ক্রিস্টোফেলস গুলো কম্পিউট করতে পারবো। ক্রিস্টোফেলস গুলো কম্পিউট করলে আমি আমার রিমান টেন্সর গুলো কম্পিউট করতে পারবো। ইনফ্যাক্ট রিমান টেন্সরও দরকার না, আমি জাস্ট ডিরেক্টলি রিচি টেন্সর গুলো কম্পিউট করতে পারবো। রিচি টেন্সর গুলো কম্পিউট করলে আই ক্যান জাস্ট প্লাগ দেম ইন my Einstein's equation and then solve the equation, and that should give me the solution of this particular field equation, right? So that's a lot of work. And if you look at my note, you will see that there are 16 crystal symbols over there. Okay, and of course I'm not going to write them all, you can just refer to them later on, but the way we compute crystal symbols, you can just do that for each variable. You can do it for r, t, and so on, theta and phi, because you have theta and phi over here. So there are particularly 4 indices we're talking about: actually t, r, theta, and phi. So you can compute all of them just by replacing indices and so on. So I'm not going to write them down, I will only write the ones that I need. So again, when you've computed the Christoffel symbols, you can plug them in the Ricci tensor and you will have a bunch of other components of the Ricci tensors as well. Again, I'm not going to write them down, I'm just going to write the ones that I need. So to satisfy the vacuum equations, the vacuum field equation, these components যেগুলো আমি হচ্ছে বের করব for the Ricci tensor, they must vanish, right? Because the Ricci tensor vanishes for the vacuum field equations. So in that case, there is one particular term which is RTR, component T, for component T and R. এটা যদি আমি 0 করি, all of them will go to 0, but particularly যদি এটাকে আমি 0 করি, তাহলে আমি দেখব that beta becomes only a variable of R. Why is that? Because when I compute RTR, RTR will look something like this. Okay, so if RTR goes to 0, that means del T of beta goes to 0. That means no temporal derivative of beta exists. So that must mean that beta is not a function of time. And since I initially বলছিলাম that beta is a function of time and R, when T and R, if it's not a function of T, therefore it must be a function of R and R only, right? So therefore this asserts that beta is a function of R. Now, furthermore, if I consider R theta theta, and I take a temporal derivative of R theta theta, we will see that this goes to 0. And what I had R theta theta as, and you will find this in my note, is e to the power of minus 2 beta R dr beta minus dr alpha minus 1 plus 1. Okay, and stating that the temporal derivative of R theta theta goes to 0, you will see that this implies del R del T of alpha equal to 0. That must mean that alpha is a function that looks like this. Now, do we understand this? Why? Let's try to intuitively understand this. So if I take the temporal derivative of alpha first, okay, that means if alpha is this, And since this is a partial derivative, the function that is only dependent on r will go away, right? So I will have something like g prime of t, right? Because it would only, the derivative will only be computed on g of t. So এখন g of t কে বা g prime of t কে যদি আমি আরেকটা ডেরিভেটিভ নেই with respect to r, then this should go to 0, because I'm asserting the fact that g prime of t is only a function of time, and therefore taking a derivative with respect to r should go to 0. And therefore this implies that alpha is a function that looks like this. By taking the two partial derivatives, this should go to 0. So therefore the temporal part of the line element, which you can see from here, a part, just the temporal part, you can boil this down and write it, which was once a function of t and r, to explicit functions individually of r and t by breaking down the alpha, right? Because alpha is a term fr plus g of t. Once you put it or exponentiate it, you can just write it as two individual exponentials, right? And this is what you get as the temporal part. This one. Okay. Now, the function of t, I can absorb this into the time coordinate, right? I can redefine the time coordinate as such and write dt as some function of g of t, as in I can write this as an exponential of minus g of t, and I can absorb this g of t into the dt squared that I have over here, and that would make my line element look something like this. Okay, so now আমি যেহেতু temporal part এর dt square এ ঢুকাই ফেলছি, now I see that indeed alpha is যে আমাদের সামনে একটা কোএফিশিয়েন্ট আছে e to the power of 2 alpha, it's only a function of r, right? So is e to the power of 2 beta, and সামনেটা তো পরেরটাতে তো r আছে, তার মানে the metric that we're considering over here, which is defined by the coefficients of the dt squared, dr squared, and d omega squared, is indeed time independent and therefore static. So this is static, and Birchhoff's theorem is therefore true. Okay, so now since it is static, আমাদের যতগুলো ক্রিস্টাল সিম্বল আমরা বের করছি, যতগুলো রিচি টেন্সর কম্পোনেন্টস আমরা বের করছি, যতগুলোতে টেম্পোরাল ডেরিভেটিভস এক্সিস্ট করে সেগুলো সব জিরো হয়ে যাবে, রাইট? এন্ড therefore we will drop all of the time derivatives from our components of the Ricci tensor particularly, and যদি সেটা হয়, then we will see that our tt and our rr vanish independently when we set all the temporal derivatives to 0. That means, and this is something that you will find once you compute it, I mean compute করতেছি না because this will take a lot of time, this particular expression of r tt and rr will go to 0. Okay, and এগুলোর যদি আমি হচ্ছে expressions বের করি যেটা আমি compute করতেছিলাম for the Ricci tensor components, this will basically give me 2 by r delta r alpha del r beta. Okay, so if this goes to 0, তার মানে আমি এই particular differential equationটাকে solve করতে পারি as a homogeneous differential equation. So basically what I will have is, right, therefore I can compute this, and the solution to this homogeneous differential equation will be, okay, and this c comes out from like as a integration constant, okay, when you integrate both sides. So a arbitrary constant টাকে আমি actually absorb করে ফেলতে পারি it might sound like আমি সব conveniently just to make things easier করতেছি, but mathematically you can actually do these things, so just trust me. So I can absorb this particular constant by taking rescaling of the time coordinate, and I can just rescale it to the constant like this. So I mean tk, I'm taking it to e to the power of minus ct, which is just adding a constant to the time coordinate, which I can do, right? So what that does is it actually tells you that alpha now is equal to minus beta. Okay. So in that case, আমরা যেটা করছি, we have now successfully reduced the number of free functions from 2 to 1. Yeah. And that makes it easier for us because, we don't have any free functions, a large number of free functions anymore. Now, next জিনিস হচ্ছে একটা দেখতে হবে, সেটা হচ্ছে যেহেতু আমরা সব রিচি টেন্সরকে 0 ধরতেছি, আর থিটা থিটাকেও 0 ধরতেছি, and r theta theta কে যদি 0 ধরি, we will see that we get r theta যেটা ছিল, r theta theta লিখছিলাম বোধহয় কোথাও, but anyway what we will get is this particular expression, which would imply that del r equals to 1. Essentially তুমি এই পুরো জায়গাটা you can write it as a derivative, total derivative term. Okay, now a lot of is done. এখন এখানে del r আমি একটা টোটাল মানে একটা পুরো একটা ফাংশন একটা পুরো ডেরিভেটিভের ভিতর পাইছি, so সেই ক্ষেত্রে I can integrate this expression, right? I can just integrate both sides from here, and integrating both sides should give me an expression for the exponential, which is given by 2 alpha as 1 by rs by r. Okay, and the rs ta ki, rs is just some constant of integration that I'm getting while I'm integrating this. Okay, এখন এই rs টা কি হবে সেটা আমরা ফিগার আউট করতে হবে. What is the physical meaning? What is the physical meaning of this rs? Okay, now remember the temporal component of the metric. So ds squared এখানে এরকম একটা জিনিস আছে, সেটা আমি if you remember last class আমি একটা weak field limit নিছিলাম as some phi function, so I can write the temporal component using that phi function, which is just the t and t component, and I can write this as 1 plus 2 phi. Okay, where phi is the Newtonian potential. So for a point mass particularly, this potential takes the form gm by r, right? So this must mean that the temporal component is in fact gm by r, right? And therefore this actually tells you that rs from here is in fact 2gm. Okay, and if rs is 2gm, you can now construct the final form of the Schwarzschild solution. So যেখানে যেখানে আমাদের এই particular formটা আছে rs, we replace it with 2gm, and finally your line element looks like which is the Schwarzschild solution of the vacuum fields equation. Okay, now one thing to note over here is that if you actually look at large distances, which means that r is much larger than rs, you will see that this boils down to a flat metric, the Minkowski specifically. কারণ যদি r much larger than rs হয়, then a term গুলো almost negligible, and therefore ds squared just becomes minus 1 times dt squared plus 1 times dr squared plus r squared, which is just the Minkowski space. And in fact, furthermore, when you do black holes, you will see that rs, which is equal to 2gm, actually is the horizon radius of a Schwarzschild black hole. Okay, so that's it for today, and that ends general relativity. Any questions?